So let's start our lecture, and then we will go to our laboratory work too. Today we will discuss local features. We have discussed them before, but today we will see more in details, more. And today I will use original slides by Ifeoma Nwogu from Buffalo. So we will talk about feature matching and extracting features. So on these slides you can see a really hard feature matching problem. This is two photographs from Mars, and can you see here something similar or not? Can you spot similar places? Can you see this picture?
We can see the picture.
Yes, all right.
So can you see similar, something similar? It's really hard, but if we will use special algorithm that we will talk today, we can match these features with this. If you look carefully, it's really look like this. And this is photo of something maybe behind this robot, or I don't know. And this is something in the forward of it. So this place and this place is the same, but it's not quite obvious from first sight. So we need some algorithm that can detect something similar in our pictures. So detect some features. So we can use this feature to match from image to image, to represent some objects, and what is requirement for this feature, local features. They should be covariant to translation, rotation, and scale. What is actually covariant? So if image is translated or rotated or scaled, so we move this image from up to left, or maybe we rotate, or even to another illumination, even change not only translation, rotation, and scale, but even to change of illumination. Then neighborhood, or this local feature should be at the same place, but moved or rotated or scaled. And it should be localizable, so we can estimate position, we can estimate it orientation and size of patch. And we also discuss this problem when we stitch panorama, when we have two similar objects. We need to find good features and find matches between them. So the same feature can be found in several images despite geometric and photometric transformation. This is called repeatability. So in this case, feature should be present here, or if something is present here, then it should be present here also. Each feature should have distinctive description, so distinctive from other features. It's called saliency, compactness and efficiency. So we want many fewer features than image pixels. So not any pixel or not any neighborhood is feature. We need not very big number of features. And locality. So feature should occupy a relatively small area of image, and this means that this is robust to clutter and occlusion. And actually, these feature points can be useful for image alignment, for 3D reconstruction, for motion tracking, for robot navigation, for indexing, database retrieval, for object recognition, for many tasks. So, for example, we can reconstruct 3D scene from several pictures. We can track motion. You know that modern cameras and modern smartphones can track some object, and for example, for focusing on it, or for optimization of image parameters that, for example, face detection. For object recognition, we can recognize, and this is not future, it's today. And last time we talked about corners and harass detector. Let's remind it using these slides, slightly different. So we need to find some corner, and key property of corner, I remind that this is region around corner. If we find region around corner, then image gradient has 2 or more dominant directions. So corners are repeatable. If we have corner on one picture, then if we change this picture a little bit, so change our point of view, then also it will be present in this corner. And distinctive, we can distinct one corner from another corner. What is a corner finding strategy? We need to find centers. On each center, estimate scale of this corner, and from a center scale, estimate its orientation. So we need to find for each feature, we need to find center, so position of this feature. We need to find scale, how big or how small it is, and we need to find estimate orientation, how it's oriented. So is it oriented up to or to down, upwards, downwards, or to the left, to the right? Okay, so so we will build some small window around the point, and slide this window in some direction. And if shifting a window in any direction should give a large change in intensity, that it is corner. So here it's flat, nothing changes. Here it's edge, changes in this direction, but nothing changed in this direction. And on corner, so significant changes in all directions. So let's discuss math something. I tell something last time, but let's discuss mathematical formulas in more detail. So we have some window W, and we have some shifting shift U and V. Then we compare each pixel before and after, and we sum up squared difference. So this is a difference of score. This is intensity of original pixel, and this is intensity of shifted pixels, and we will sum up it on this window. Okay, so but how we can estimate our shift? To estimate our shift, we can use Taylor series expansion of this intensity, and we understand that shifted intensity is some intensity of original, and then this derivative multiplied on shift in one direction and derivative in other direction, and multiplied by shift other direction. And plus some higher order terms. If shift is very small, then first order approximately will be this one, using this formula, or in matrix view, this. If we then use this formula, then we obtain this one, or it can be rewritten as this. And here is this H is our structure tensor that we talked last time. I remind that it looks like this. So then how we can understand which shift will give more value. And to this, we can use algebra, quite advanced algebra, linear algebra, and we can use aging values and aging vectors of this matrix. So I remind you that aging vector, it's some vector x, that multiplication x on matrix is equivalent to multiplication x on some number. And this x will be called aging vector, and lambda, this scalar, so this is some number, is called aging value. And we can find them using this formula, and here is our solution, but we are not very interested in this solution, but we understand that they are present. Well, let's talk about meaning of these aging values and aging vectors of this age matrix. So if we will talk about difference largest and smallest shift and largest shift and smallest shift, then direction of largest increase will be this x. We can this is aging vector x plus, let's call it x plus, and its corresponding aging value means amount of this increase in this direction. So intensity will change very rapidly in this direction, and we can use other direction, and we can use its perpendicular direction, and when we can use its aging vector, that means direction, and its aging value, that means amount of increase in this smaller, in this perpendicular direction. So let's find example on this checkerboard image. If we take this checkerboard image, then at most points we have no. So this matrix is actually zero, because if we take some point inside this cell, not on boundary, not on corner, then nothing changes if we move our window up or down or in any direction. But if we add age, then we have large lambda plus. So lambda plus will be large number, because in this direction we have a big change of intensity. But in this direction we have no change. So lambda minus is 0. So lambda plus is big at these edges, but lambda minus is 0 at these edges, because only one in one direction. So only bigger lambda is positive, also is big, and smaller lambda is 0. But if we take corner, then in both direction we have a change of this image. So if we take this sliding window and shift it up, down, left, right, then we will experience a rapid change. So only in these points we experience large value of lambda minus value. So what should we do to detect our features or corners? We should compute the gradient at each point in image. We should create this age matrix. We should compute eigenvalues, and we should find points with large response where lambda minus is large. And we should choose these points where lambda minus local maximum as features. But it's better not so. I have shown this picture to you. So if we have both lambda values small, that we have flat region. So this matrix is almost constant. So it's almost 0 in all direction. If we have one number, so lambda 1 or lambda 2 that is big, we have change only in one direction and nothing in other directions. So we have edge. But if both numbers are large, and very important, then not only large, but approximately similar. So we have change in all direction, and these ellipses look like big circle. Then we experience corner, or in this case K point feature. So we can extract feature from this K point. But why we need two numbers if we can use one number? We can use simply one number R that can be computed using this formula. So determinant of matrix minus alpha multiply by trace of matrix in square. And this can be rewritten as this. And if we have small absolute value of this corner response function, that we have flat region. If this response function is less than 0, we have edge. And if we have R corner response function is non-zero, is positive and big positive, bigger than some threshold, then we decide that it is corner. Okay, let's find out which steps do we need to use Harris detector. We should compute Gaussian derivative at each pixels, compute second moment matrix, this matrix H, in some Gaussian windows around each pixel, then compute corner response function R, threshold R, and then find local maximum of response function. So if we have several points with big R, we should leave only maximal points with maximal R. Let's see these steps on these two pictures. So we understand that this is two pictures of the same object, and we should find features of this object, and they should be the same, but only shifted or rotated. Let's see how it works. At first, let's compute corner response. And here, blue means negative, some negative value, or red means some positive value. So we see that we have blue on edges or for example, red on some corners. Then we should find points with a large corner response. Okay, so we find these points. Very good, but it's too much. So we understand we don't need such number of points. So we need to take only points of local maximum of R. So in each region, we take only maximal value in some neighborhood. So we have these points here, and these points here. And if we draw them on picture, then okay, so we can find that these points are really, I don't know, it's not like simply corner. It can be cross of this, of two something. It can be corner like this. It can be something like crossing two, or some one feature meeting other, no, one edge meeting other edge. So, but this is good points to take them as key points. Let's consider invariance and covariance. So we want features to be invariant to photometric translation, so changing of lightness, and covariant to geometric translation. Invariance: if image is transformed, then features should not change. So if we change lighting, so here is more light and here is more dark, nothing changes, and this is good. Covariance: if we have two transformed versions of the same image, features should be detected in corresponding location. So if we have a feature here, then if we change it, it should be here, for example, or this feature from here should be, for example, here. So this feature change their position, but change with the whole object. So let's consider image translation. So derivative and window function are shift invariant. So derivative doesn't depend where this is situated, in which part of image. So we make conclusion that corner location is covariant with respect to translation. Very good. Image rotation: if we have some corner and we rotate it, of course, we change this matrix H. So second moment ellipse changes, it rotates. But very important that its shape, so eigenvalues remain the same. So this one eigenvalue and this second eigenvalue, lambda plus and lambda minus. And here is lambda plus and lambda minus. So it's rotated, so eigenvector rotated, but eigenvalues doesn't change. So corner location is covariant with respect to rotation. Very good. And scaling: we have this corner, we scale it. Unfortunately, we have problem. Here we have rapid change. So when corner was quite small, then we have a rapid change. So we have corner, but when we scale, it look like this, and it's not as sharp as it was anymore. And if we take any small region, then we find, no, it's not corner. No, this is not corner. This is not corner. This is not corner. It's all edges. So it's very, very, how to say, slight. So smooth. It's not as sharp as it was here. So corner location, unfortunately, is not covariant to scaling. So this is not very good. So we can say that Harris corner detector give good corners with high contrast and sharp change of intensity. Image features at good corners means that we have large gradient that change on two direction. So we have two large eigenvalues. We can compute this matrix and find corner response function. So what problem still do we have? So edges and corners, we talk about edges and corners, they convey boundary information. But what about something in the middle of image? So about some interior feature, texture of objects. And we use next. So this is we will use next slides from Ifeoma Nwogu, local features continuation, and we will talk about detecting blobs. So we start from Harris corner detector, but today we'll talk about blobs. So what is actually blobs? It's some region that differs from its surrounding, and it's very distinctive in its form. So we can find here some blobs, and it can be bigger or smaller. So we can describe this blob as some circle with something that is different from its surrounding. So our goal to achieve scale covariance. So to independently detect corresponding regions in scaled version of the same image. So we need some scale selection mechanism for finding characteristic region size if it is covariant with image transformation. So we have two images, and this is zoomed in, and this is zoomed out, and here our object is bigger, here it's smaller, but we should detect it. So some descriptor of this object should be the same, but scale of this object should be different. Okay, let's move to this goal. I remind you that if we want to find edge detection, we can take the Is it okay? So you can you see my slides? Can you hear me?
Yeah.
Yes.
Okay. Okay. So I hope that you remember about detecting edges. But we have not only derivative of Gaussian, but we have also Laplacian or second derivative of Gaussian. It's called Laplacian of Gaussian. If we take this Laplacian of Gaussian, then what happens? So here we have some image with some noise. Here we have edge. Here we have this so this is signal. No, in this case it's more simple, just one-dimensional signal. So this means change of intensity. Here we have this one-dimensional second derivative of Gaussian filter. This is kernel. It's look like this. Second derivative of Gaussian. And then after applying this filter, we will have 0, 0, 0, 0, then a rapid increase, then very rapid decrease, and then increase, and then also 0. So we have edge where we have 0 crossing of second derivative, where second derivative is big on one side and is very small, or positive on one side, negative on other side, and change very quickly. Okay, then let's take, if edge is some change of intensity, then blob is superposition of two edges. So we have something small, then big, then small. And let's use this Laplacian of Gaussian filter. So we have here and here, here and here, such figures. If we make closer, then they make closer. So at first it was size from 10 to minus 10. So size of this blob was 20, then 14, then only 6, and you can see that it almost superposition. And if size of this how to say, size of this blob is equal to 2, then, and we will convolve with Gaussian with this sigma parameter equal 1, then we can see that these two, how to say, these two part of graphs, they are in the same position. So we have very rapid and very strong decreasing of value here. So we can detect that our object happens here. So we have maximum of maximum of absolute value. It can be here or it can be here, doesn't matter. So maximum of absolute value of this intensity after filtering. So the magnitude of Laplacian response will achieve a maximum at the center of the blob, but not in all cases. Only if the scale of Laplacian is matched to the scale of the blob. So right here, we have no such property, but here we see that it works. So let's assume that we have detected a corner. So we detected some, how to say, some place that we think feature can happen. So how big its neighborhood? We can use Laplacian of Gaussian filter. So our strategy is apply Laplacian of Gaussian at different scales at corner. Choose the scale that gives the largest response, and this will be covariant with respect to scaling. So we want to find this scale of blob by convolving some signal using this Laplacian at several scales and looking for maximum response. So we change our sigma, so we increase sigma. So we have signal. With sigma 1 we have good picture, but this is not very good sigma. So because as you can see, these don't coincide, so they differs. They should be at the same place. So here is closer, here this closer, but unfortunately you see that response is smaller. Here response is even smaller. Here it's almost zero. So why this does happen? So the response of derivative of Gaussian filter to the perfect step h decreases as sigma increases. So when we blur this edge, so derivative will be less. So the derivative decreases. So to keep response the same, so scale invariant, we must multiply Gaussian derivative by sigma. But Laplacian is actually the second Gaussian derivative. So it must be multiplied by sigma squared. So if we take an normalized Laplacian response, nothing interesting happens. But if we use scale normalized Laplacian response, so the same but multiplied by sigma square, then we will see that size of this ridges, of these changes of intensity, the same here and here, and actually the same here, but here we see superposition, and when sigma is equal to 8, we have ideal superposition, and we have maximum of response, and then sigma is too big, and we have no this maximum. So we can say that our size is equal to 8. But actually it's not equal to 8, but it's equal to 16, but radius is equal to 8. If we take radius, if you approximate this as some circle. Okay, so what is in two-dimensional space? Laplacian of Gaussian look like this, and calculating using this formula. So it's circular symmetric operator for blob detection in two-dimensional space. It's look like this if we draw it. So it's black inside, it's light, so it's very big negative value inside. Some small positive value here, and 0 in all other places. Then we find scale normalized. So we multiply it by sigma square. And if we take image that is actually binary circle of radius r, and we apply Laplacian, and we find when it's coincide, then maximum response occur on this sigma that equal r divided by square root of 2. So we define characteristic scale of blob as scale that produces peak of Laplacian response in the blob center. So because of this, we can find scale of our object. Okay. So we need to convolve image with scale normalized Laplacian at several scales and find maximum of squared response in scale space. Let's see example. We have here, what do we have here? We have small sigma. In this case, maximum we have for small features. So small features give large response, but big features give smaller response. Then we increase our scale, increase once more. You can see that we can detect these quite good, even better, maybe maximum here. So we can detect this very good, but not this, not this, not this. And by increasing our sigma, we can see that right now it's optimal for this or this feature of our butterfly wings, or this, but not for this, for example. These are too small. And then we can find these big features and even bigger. And if we draw our result, then we find small features and we find big features and we find actually we find each feature, each blob with its size. If we want to efficiently implement this, then actually Laplacian is quite hard formula, but we can approximate Laplacian by using different of Gaussian. So instead of finding real Laplacian, we can find difference of two Gaussian on different scales if we take appropriate k. So because of this, what we can say about invariance and covariance? So Laplacian blob response is invariant with respect to rotation and scaling, and blob location covariant with respect rotation and scaling. So it's quite good. So let's make some short summary. So assume we have detected a corner of some feature. How big is neighborhood? So we can use Laplacian of Gaussian filters. We can apply it on different scales, choose scale that gives a large response, and this is good. And this is our function. This is Laplacian, this is Gaussian, this is Laplacian Gaussian formula, and we will convolve it to image. Okay, but right now we understand how find place, how find scale, but we need to find rotation at first, and we need to describe it so we can differentiate different features. And we will use idea of David Lowe that he gives on 2004, and he calls it scale invariant feature transform. So the basic idea is to take 16 by 16 square window around detected features and compute edge orientation. So what is edge orientation? So it's angle of its gradient. So if we find gradient in each this square, then for each pixel, we can find angle angle of gradient, angle of gradient minus 19. So perpendicular at angle of gradient. Then we need to throw out weak edges. So when this gradient is very, very small, we don't count them, and create histogram of surviving edge orientation. So we have different orientations, and we see that more popular this orientation, but other orientation also happens. So to efficiently implement it, we see that we can find difference of Gaussian and different scales. So we can scale our image, bigger image, then scale it lesser, lesser, and lesser. And different of Gaussian also scales the same. So sample point is selected only if it is minimum or maximum of these points, so extremas of these images. We can localize, using these formulas, we can localize our point. And we can find orientation. So when we compute this descriptor, we compute it relatively to k points orientation. So we should find dominant orientation, so dominant gradient, and rotate it. So each orientation should be considered relatively to main orientation. Then we find orientation histogram. We position an orientation each gradient sample rotated relatively to k point orientation, to main orientation. We weight magnitude of each sample point by Gaussian weighting function. And then we use several bins. We normalize the result to unit length and cap each elements to this value and normalize again. So what we have in result? We have 4x4 bins, special bins, 16 bins in total. We have Gaussian center weighting here. We have 8 bin orientation histogram per bin. So for each bin, we will compute 8 orientation. So we have 128 dimensions in total, and we normalized them to unit norm. In such form, we obtain final result by taking all these histograms, as I said, normalized, rotated relatively over main key point, such that we obtain this descriptor. How we can match them? Let's find. I here can show you the picture. If we have two histograms, that is called X and Y, of two features, how we can find are they similar or not? So each histogram consists of this intensity of number of and summary of gradient in each direction. And then if we compare it's then as it is rotated through main key point. So first histogram column should be biggest. And as it's normalized, we can just find difference between all values of two histogram, make this squares of this, and sum over this histogram, and this is called L2 norm. So it's sum of squares of each values. If we take just sum of modules, absolute values, then it is called L1 norm, but L2 norm is more popular. So if we take this shift, we have this shift algorithms. It detects key points and descriptors. So as I said, it uses a difference of Gaussian as approximation of Laplacian of Gaussian, and it uses different scales. It uses two scales, sigma and k sigma, and then this process is done for different octaves. So scale for first octave, then scale for next octave, and etc. And we find this pixel, we localize its k point, we find orientation, and we descript these k points, and so we can then match this k point. So how we should do? For example, if we have some image, we read it from disk, then we can convert it to grayscale, because shift works for grayscale. We can initiate this shift algorithm, and then detect and obtain these key points. So special method draw key points, draw these key points on this image. It looks like this. You can see that this algorithm finds different key points of different size and different orientation. So it's too much here. Okay, but what if we want to match them? Okay, let's find out. So let's find out our second laboratory work. I will go here to our team, to our assignments, and I will import our laboratory work too. So I will import from last year course, a laboratory work 2 that is called feature extraction and matching. Okay, so I need to give some deadline. Okay, let deadline be maybe not next. Actually, we need to give some more strict deadline because our course maybe not next week, but okay, 2 weeks. Let it be 2 weeks for all students, 15 points. And what actually should we do? And why it's such small font? I don't know. Can I do it bigger? Okay, so what should we do in this laboratory work? We will work with OpenCV to perform feature extraction and matching on pair of input images. Our task to write Python program that reads input images, extract features using some algorithm, and matches the corresponding features between two images. So you will then display the matched features and output result in visually appealing way. So we can understand either it's good or not. So our requirements: to write Python program that reads pair of images and display on screen. Then use OpenCV to extract some features from images. We can use, for example, SIFT that we talk right now, or some other feature extraction algorithm like SURF, ORB, etc. Then we should use OpenCV to match the corresponding feature between two images. So you should use at least one matching algorithm. So we can use several if you wish, but you can choose one algorithm. For example, brute force matching or plan matching, etc. And we should display the matched features between two images. So you should draw lines or circles to connect matched features and display them on original images. And we should do it for at least 2 pairs of images, but maybe more pairs is better. These images should show the same object, but in different environment, angle, size, illumination, etc. So you should provide Python code with several pairs of input images and the corresponding result of feature extraction and matching to your report. But maybe I should, at some point, we should analyze these matches. Either they are good or not. So you should analyze I will show you examples right here. No, don't worry. So, and provide Python code. So here is some instructions. You can use im read, then cvt color, then sift create, then sift detect and compute, then cv2 bf matcher, for example, brute force matcher, then use match, some sort matches by distance, and draw sort maybe let's more and take best, only best matches. Because if we draw all matches, I can show you if we draw all matches, we will have too big. So if nothing will be clear. So we should take only best matches, only the best matches. Draw matches, matched features, and display result using CV show. In this example, we use sift and brute force matcher. You can experiment with other feature detection. For example, if some feature detector work not good, you can take some other feature detector. So this is our assignment. I press assign key. So we have this laboratory work too. And okay, we will see how it look like. Should we? Okay, we can do it right now maybe. I understand that we take too much time, but let's do it right now. And then we will make a break. Okay, so actually I have done this work. Let's open. So this is this work. I open with idle. Okay, what do we have here? Oh, this is importing of OpenCV, nothing interesting. I read two images, then I maybe change them. Then I convert these images to grayscale. I initialize sieve detector and I detect key points and compute descriptors for both images. For both images. Then I make some matcher. I match descriptors with each other. So what is actually matching of this descriptor? How this BF matcher works? So we can find brute force matcher. It takes descriptor of one features in first set and matches with all features in second set using some distance calculation. And the closest one is returned. And we should use some norm. By default, it's norm L2. It's good for sift, surf, and etc. For binary descriptors, it's not very good. Okay, so sorry, I Okay, so let's continue. Sorry for interruption. So we talk about feature matchers. So and about norm. As we use shift, we is okay for this norm L2. But if you use orb, brief, brisk, etc., so binary string based descriptors, maybe it's better to use norm Hamming or norm Hamming 2. And cross check is false by default. And if cross check is true, then matches return only matches that are mutual. It means that if shows pair I j only in this case, if some descriptor in set A is best match for descriptor in the set A, B, and vice versa. So these features should match each other. Maybe it's better to use cross-check as true. So if provides more consistent result. If we use these parameters as true, it's better for us. And then we can use draw key points to draw these key points and draw matches to draw matches. It's tagged to image horizontally and shows first image and second image with best matches. It's look like this. You can see. So we can use some matcher with cross check, for example, true, then match descriptor, then sort descriptor in order of their distance, and draw first best matches. When we sort, distance is in optimal if two features is the same, distance will be 0. But in real life, distance never will be 0, but it maybe will be close to 0 if match is good. So we can match, for example, this picture to this picture. As you can see, we can find here some features and match them here. Okay, so but let's see that I use norm L2 and I use cross checking. I match descriptors and sort them in order of their distance and draw. Here I draw 20. Okay, let's revert to 10 matches and show this result. Okay, let's start our code for two pictures, tulips small and tulips rotated. I run it, and this is, you know this picture very good because I showed you very many times, and this is just a picture of these tulips, and I rotate this picture in image editor and obtain this picture, and of course it's very easy to match features on this picture. So as we know, it should be consistent with this scaling. Oh, with this rotation. So in covariant with rotation. So what is means covariant when with rotation? With respect to rotation. If feature is here, then after we rotate picture, then feature is rotated as well. This picture rotated as well, etc. As you can see, that is very good matching because it's very easy problem. Okay, let's take more hard. Let's take here. What do we have? Let's see our pictures that I prepare. What we can also match. I have these two pictures of our panorama. Do you remember? I just take this picture. I just extracted them from slides, and of course we can match some points on right of this picture and left of this picture. Let's see. Can our program cope with this? Take panorama 1 and panorama 2. Run our algorithm. And as you can see, we have very good matching quality. It seems that all matches is correct. So we can use this for stitching our panorama. What else we can do? Can we match, for example, picture with different, how to say, with different contrast? But let's take smaller pictures. So here is not equalized variant. Not equalized variant to this equalized. Why I use for small pictures? Not because it doesn't work for big pictures, it's work very well, but I can show only small pictures because otherwise our window should be bigger. It works also very good. It's also very straightforward. I can match, for example, tulips rotated to big tulips rotated, tulips. How? Okay, let's find that. Here is tulips, simply tulips, JPEG, tulips. Very big image without this noise. You can see no noise here, and big. And tulips rotated is noisy and it's small. Let's run it. Can it work? As you can see, it easily can work. Match this for this here, this. This very close matches. These two matches are very close, but they are in appropriate places. This is also normal, and this is also good. This is good. This is also good, and this is also good. So as you can see, it works again quite good. So it can match smaller and rotated image with bigger without any problem. And really challenging task. It's two photographs, completely different photographs of Pisa tower with different, maybe different scale, with maybe different point, with different, you can see some repair works here, but not here, and different illumination. But why it's very hard? Because here we have regular structure, and because of this, because of regular structure, it can have some problems. So here is good match. It seems that good match. So it's match, it's correct. But here, for example, it match this from upper to down. It's not correct. It's totally not correct. This match maybe is correct, which we need to check it. But for example, this match is totally not correct. This match is totally not correct. It match some building with Pisa Tower. Totally not correct. This is not correct also. It match lower lower part of this tower to upper part. I understand that it's look like, so it's like structure with some periodic parts. In this case, it's very hard to match. So we can see that our SIFT algorithm work pretty bad here. And let's consider some protocol of last year students. Okay. We can find some results of last year and find result of third work. I don't know, it's not third work. It's not third work. It's not for third work. And this is not third work. It's second work. Second work. Oh. So this is results by last year students or Hedzi, and he takes several images. For example, he also take two images of Pisa Tower, and he calculates. You need to calculate for each image. You can take several key points and estimate how much points are good and how much are not good. For example, total 15 points we take, 6 are correct, and 9 not correct. So here we have 2 images and 14 are correct. So it's just rotated. It's just that image that is rotated. It's much more simple task. It's very easy if it's just altered image. Very easy to do it. But if we have, or in this case, when we have 2 images, but our image, but deformed image is a part of this image, so we can easily, so it's also quite easy work. But maybe even here 2 points is not correct. For example, this point, I don't know why it's not correct, of course. So you should give your code, should give your images, source images that you use for comparison, and you should give this image like this one. I can easily save it. Save. for example, results. How it said results? Let's say results. Example. Compare feature matching. Feature. Let's go feature matching. For example, PNG. And let's save this EMG3, for example. Can use save to create this result. Why it doesn't work? Not in save. How it should called? In write? In write, maybe not in save. Sorry. In write. In write, and at first should be okay. First should be file name and then image. So first file name. So I write it correct but wrong name. In write, not in save. In write. Right. So I can save our result. I can save our result. So this is our result. I can open it using, for example, fast on image viewer, and here is our result. So I can use my zoom tools to check it correct, to check each feature in details. So you need to provide this image in your protocol like this. I hope that this work is quite clear. Do you have some question on second laboratory work?
No, it's very good. I understand it. Thank you, Professor.
Okay, so in this case, let's see about first laboratory work. So we have several results, and we will see them, but after short break. So right now, short break, and then we will see your laboratory work results. Is it good? So short break, 10 minutes, and then we will check lab 1 results. No, some new students, some new results of laboratory 1. So I stop recording and we make this break.